Okay, we should commence. Um, so, battle plan for today is questions about induction-y stuff. To actually finish exercise 12.11, we started it on Friday, but we need to wrap it up today. Then, if time allows, we can start talking about some other kinds of induction problems. We'll do one that's sort of like a divisibility problem about making change with coins. And then if there's still time, which seems incredibly unlikely to me, we could talk about Fibonacci numbers and recursively defined functions. Um, so, uh, so we'll start with the the divisibility problem. But before we do that, does anybody have any questions they want to ask about any of the stuff that we've done so far?
Um,
Go for it.
for axiom or theorem 8.23a, when we do split off term on stuff,
Yep.
is the split off term n plus 1 and not just regular n?
Well, so you have to be a little thoughtful about split off term and what you want to do with it. So that's a great question. I know at least a couple of questions I got sort of over the weekend were in some way related to exactly what split off term did. So let me, grab my copy of the thing here. So let's look at exactly what split off term says, and then we'll think about what that might mean. So theorem 8.23, split off term, whatever. And I'll just focus on A, but all of this applies in varying ways to B as well. So split off term says star I 0 at most I less than n plus 1 p equals star I 0 at most I less than n p star p I gets n. Okay. Now this is one of these places where if you can, if you're careful, just follow the rule. But it's useful to understand kind of why things are the way they are, because it makes it easier to deal with unexpected situations. So, as an example, well, here, let's think about this first. So this is P of 0 star P of 1 star dot 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 P of n minus 1 star P of n. And it stops at n because we are less than n plus 1. So we go up to n, but we don't go to n plus 1. Okay? And so then this part ends up being this, and this part, the P of n, saying this part and not being able to point at something is not super helpful, ends up being this guy here. And there's always this question of, well, like, is this, when I do split off term, am I going to get an n here or an n plus 1 or an n minus 1? And you can always like manipulate these ranges so that this has the form less than something plus 1, and then this will be the something, whatever that is. But you can also just think carefully about, well, what is the set of values this range gives me? And what would, in particular, what's the last value in this range? And that's gonna be the thing that I split off. and then I'll have everything else in what goes before it. And so as an example, if I have let's say, so this is going to be exercise, and I won't do the whole exercise, I'll just focus on the split off term part. But 12.4c, it says the sum of I, 0 at most, I less than n, 2 to the I. Now here, when we do the induction step, we're going to put an n plus 1 in here. So sort of in the induction step, we're going to end up with a sum over I, 0 at most, I less than n. Oh, n plus 1. That was the whole point of the exercise. Doing n plus 1, 2 to the I. And now here, because this matches 3.823a exactly, this is going to rewrite as sum over I, 0 at most, I less than n. That's this bit over here, 2 to the I, plus, because summation is plus, and then the body with I equal to n, so we'll have 2 to the n here. Okay, so this just follows the theorem really, really cleanly, and everything is nifty and swell. However, we also have exercises that don't behave like that. So as an example, if we looked at F, exercise 12.4F, we have the summation of I, 0 at most, I, and now here we have less than or equal to, right? That's different than here where we have a less than. And I times 2 to the I. Okay. And so in the induction step, when we add 1 to n, we're going to get the sum over I, 0 at most, I at most, n plus 1, I times 2 to the I. Now here, this does not match 8.23a anymore, because 8.23a has a less than here, and we've got a less than or equal to. So there's a couple of options. We can do this, sort of make this formally match up, and that's what I'll do now. But you could also just look at it and say, oh, the last value in this range is going to be n plus 1. So I want to split off a p with I gets n plus 1 here. Instead of an n, I'm going to want an n plus 1 as the last guy, because this goes up to and includes n plus 1, whereas this went up to but did not include n plus 1. Okay? But if that kind of informal thinking makes you anxious, which is a legitimate position to be in, I can do a little algebra here. And let's see, what would that look like? I'm using the fact that x less than or equal to y is equivalent to x less than y plus 1 for integers x and y. So I could rewrite this as the sum over I, 0 at most, I less than n plus 1 plus 1. So if it's less than or equal to n plus 1, it's less than n plus 2. And I've written it sort of this way, both because that matches this little rule, but also this then lets me match the less than something plus 1 up here, where the something now is this n plus 1. And so now I can use 8.23a directly, and I get the sum over I, 0 at most I less than n plus 1, I times 2 to the I. And now I'm going to have P with I replaced by n plus 1. So I'm going to have, oh, I'm running out of room, n plus 1 times 2 to the n plus 1. And so it's crucial here that I get the n plus 1s here, because this went up to and included n plus 1, whereas over here it didn't include n plus 1, it stopped at n. So I only ended up with an n here, and I ended up with n plus 1s over here. And that frequently kind of befuddles people. And I'm guessing that that's the source of your question. If I'm wrong, I've just spent a long time talking about something that wasn't useful. So hopefully that was the right thing, question mark?
It was definitely the
Okay.
right thing. So then the range doesn't change?
The range doesn't change. I'm not sure I understand which range are we
Oh,
talking
wait,
about?
never mind, it does. So it changes from being less than or equal to n plus 1 to less than or n plus 1.
Right, which
For
notice
this
that to
split-off
make
term.
this match here, because we want to come back and match this, we'll use this fact again to say that this is equal to, by the same algebra fact, that guy there, that this is the sum over I, 0 at most I, at most n, I times 2 to the I, plus n plus 1 times 2 to the n plus 1. And now this matches our induction hypothesis, and we can replace that with the right-hand side, and hopefully then do a bunch of algebra to simplify. So you do have to be careful to make sure that you match 8.23a properly or use it properly, and that if you do something like this to manipulate the range to make 8.23 match, you may have to unmanipulate to get it to rematch your induction hypothesis again. Does that make sense?
Yeah.
Questions about that for folks? That was a great question, and this is a place where people often get stuck. And I know, yeah, I know at least one person was having trouble with the base case, because another place where this matters is if we think about a problem like this, here, if we put 0 in, let me change the color. Here, if we put 0 in, 0 at most I less than 0, well, that's false. And we can use the empty range rule. But here, if I put 0 in, we get 0 at most I at most 0, which is actually equivalent to just I equals 0, right? That's not false anymore, because there is an I that makes this true. And then instead of using the empty range rule, you're going to want to use the single point rule, which is 8.14. So here you would use single point rule 8.14, whereas here you would then use the empty range rule 8.13. So you do have to be careful. So on the one hand, the induction proofs can be fairly mechanical, but there are places where you do have to be, if not like, they don't require brilliance, but they do require awareness, I think is maybe a way to think about it. So you have to be like what actually is true here? Which rule does that mean I can use? Or in the case of the split off term, am I using split off term correctly? Am I splitting off the correct term? Am I keeping my range so that things match my induction hypothesis, et cetera, et cetera?
So then, if I'm understanding the single point rule,
Yep,
would that have ended up just being, like in the example, or in your exercise 12.4, would that have ended up being 0 times 2 to the 0?
correct.
Okay.
So single point rule says if you only have one value in the range, the quantification reduces to the body with that one value plugged in. And since this is simplifies to I equals 0, we would just put 0 in for all the i's here. And this whole quantification would become 0 times 2 to the 0. And there are, so of the examples in 12.4, there's 7 examples, and 1, 2, 3, 4 of them have less than or equal to n, and 3 of them have less than n. And so 4 of them you would kind of do this way, like I talked about with F, and 3 of them you would do this way, like I talked about with C. And the book's not just being like obtuse or difficult in some way, right? The things that are true, right? And so if it turns out that a certain thing is true when I is less than or equal to n, well, that's just when it's true. And if another thing's true when I is less than n, well, then it's true, right? So the book's not just trying to mess with your heads here. These are just the truths that happen to exist. So that was a fairly long example or answer. It's not really an example, an answer to a question. Did that sort of get at what you were asking about, Justin?
For sure.
Okay. Anybody else have any questions on that? Because that is a common source of confusion and or frustration. So definitely feel free to ask. Going. Any other questions before we return to exercise 12.11?
I was wondering, I'm having a little bit of trouble setting up base cases.
Okay.
So like for 12.4c, would
Yeah.
you do 2i to the 0 equals 2i and I equals 0 equals 2n, which is 0 minus 1? That's true. Is that how you would set up that base case? Or
Well, you would set the base case up. Here, let me actually make a new page for that. So if I claim, well, let's actually we'll look at F again. Well, no, let's not look at F because that's not really the one you asked about. So let's we'll set up C, 12.4 C. Yeah, okay. Had a minor panic attack that I'd forgotten to record, but I'm recording, so we're good. So the claim is that the sum of I, 0 at most, I less than n, 2 to the I equals 2 to the n minus 1 for n at least 0. So the base case is going to be n equals 0. And we know it's 0 because that's the smallest value that this is supposed to be true for. And all you do is you plug in 0 for all the n's. So you need to show that need to show that all of this is true with n being 0. So you would plug in 0 for all the n's and then show that that's true. And for the base cases in the problems that we're looking at, this is almost always either empty range (8.13) or single point (8.14). And then this is just usually some simple algebra or arithmetic. Now, I don't know, did that answer the right question? I don't feel like it maybe did.
It did, yeah, because I don't know how to like set them equal to each other or like plug in the ends. It did. Thank you.
Not a problem. Glad to have helped. Other questions before we move on to exercise 12.11 again, or return to exercise 12.11. Going on. Okay, so our friend exercise 12.11. So 12.11 says prove that 4 to the n minus 1 is divisible by 3 for n at least 0. Now, we had started this off on Friday. I'm actually going to redo the whole thing because I think all we'd done was the base case. And so I'll go ahead and redo the base case, and we'll work through, we'll talk some about like what does it mean to do the induction step, and then we'll work through the induction step and finish the proof off. This is, so I would argue that the divisibility problems and the coin problems, which we haven't done one of yet, but it would be where we would go after this. And the coin problems and divisibility problems are both exist problems. And that these exist problems are probably the next to the last particularly difficult thing that we'll talk about this semester. I mean, there's like a handful of things that over the course of the semester that I think are like intellectually difficult as opposed to just tedious, right? If that makes sense. And I think these exist problems are in some meaningful way difficult. Like there's a lot you have to understand to be able to sort of follow the proof. And so on the one hand, we're getting close to the end of the hard things as Nick defines hard, which may or may not match to your definition of hard at all. And I, can't do anything about that. But we're getting toward the end of the hard thing. So that's a good thing. On the other hand, this is a hard thing, a less good thing, right? But I would encourage you to definitely ask questions about this as we go, because I do think there's a lot going on here that is not simple. And so you should feel free to be like, what are you talking about? Okay. So as we talked about before, what is it? How do we formalize this? We're going to formalize this as there exists a k, I should say for n at least 0, there exists a k in the integers such that 4 to the n minus 1 is 3 times k. Okay. And so this is how we're going to handle this divisible by 3 business. Okay. And so this is essentially P of n. Are you with me so far?
Yes.
Cool. I appreciate the vote of support. proof is where I want here. Proof by induction on n. Now, the base case is going to be P of 0. And we know it's 0 because we're going from 0 up. Okay. So we want to prove, so we need to show that exists K, Z, so an integer K, where 4 to the 0 minus 1 equals 3 times K. So we're saying we need to show that there is some K that makes this thing true, okay? And what we did on Friday is we basically kind of just did some algebra on the side and used exists introduction to then tidy things up. That worked. I'm actually going to do it a slightly different way today that's, I think, more formal, but also less likely to get you in trouble because it's less about intuition and more about like using algebra. And we're all awesome at algebra, so using algebra sounds fun, right? Yeah, okay, fine. So by exists introduction, which is 9.28, this is true if we know that 4 to the 0 minus 1 equals 3 times K is true where K is substituted, replaced with some expression E. So that's what 9.28 says, is if you know something's true for some particular value of this variable, then we know there exists a value that makes it true. If something's true when K is 7, then we know there exists a K that makes that thing true. If I know someone has a nickel where someone is coal, then I know there exists a person that has a nickel. Okay, and so I can say this follows from that. That's just a direct use of 9.28. And then I can use textual substitution. To stick E in for K, and I get 4 to the 0 minus 1 equals 3 times E. And now, to finish this, I just need to show that E really exists, that there is an E that makes this work. So in some sense, I just need to solve for E. This is a classic Algebra 1 problem from high school where I've got a variable and I need to solve for it, okay? And so if I can solve for this, then I know there is an E that makes this work, which means I know there is a K that makes this work, which means I know there exists a K that makes this work. And so from here on out, it's all just algebra and arithmetic. So this is by arithmetic, 4 to the 0 is 1 minus 1 equals 3 times E. And I'm going to zoom over here. And that is then, well, 1 minus 1, we all know what that is. Like I'm writing this out probably in more detail than you would need to. 0 equals 3 times E. And now I can just divide through. Divide both sides by E. Or by, not by E, by 3. Dividing by E would be problematic. In particular, I couldn't divide by E because I don't know that E is not 0. and dividing by 0 would be bad. But I know 3 isn't 0. 3 and 0 are different things. So I can say 0 divided by 3 is 0. 3 times e divided by 3 is e. And so e equals 0 implies or exist. Okay? So e equals 0 makes 4, 0 minus 1 equals 3 times 0, 3 times e true. So by 9.28, we know that there exists a k in the integers. Oh, and it's, bad me. It's important, and I should have been more explicit about this. It's important to notice that e is an integer. That when we solved for e, we got an integer because we need k to be an integer over here. And so this being an integer here means that we have to check that the thing we got when we did our algebra was an integer. And it wasn't like e wasn't 3.5 or pi or the square root of -1 or something that is not an integer value. But because this is an integer value, we're okay here. So then we get that, and we're done with the base case. And we're done with the base case. Boom. Okay. Questions about this? So we want to show and exists. We use 9.28 to say, hey, that is, that would follow from the body being true with some expression in for the quantified variable. Then we use algebra to figure out, well, what is that expression? And if we find a solution that has the right type, and you could fail to find a solution, like maybe there just isn't one, or you could find a solution that's the wrong type. So you do have to be a little thoughtful about this. But in this case, we found a solution and it had the right type. And so we're done. I mean, really, I didn't need necessarily to repeat all of this. I think we could have gotten here and just said, and we're done with the base case. But this just sort of recaps what this all means sort of upside down, that this makes this true. And then by 9.28, that implies this. And that was the thing we were trying to show. So strategically, use 9.28, get the expression in, use algebra to solve for the expression, check that it's got the right form and type. If it does, then you're done with the base case. Does that make sense? Do people have questions about that? Okie dokie. We are going to move on to the induction step. Boom. Yeah, I'm just going to make a new thing. So, so induction step. P of n implies P of n plus 1. What does that mean here? That means there exists k in the integers where 4 to the n minus 1 equals 3k implies, same thing, there exists a k, probably a different k, but there is a k in the integers such that 4 to the n plus 1 minus 1 equals 3 times that k. Okay? I guess I should have had a little dot here. Okay. So now what does this say? This is saying that if there is a k that makes this work, so if there is a k that makes this work, then there is a probably different k. Doesn't have to be, but I'm not sure I can think of an example where it wouldn't be. That makes this true. Okay. So we're saying if we can find a k that works here, then there is some other k that makes this work. Does that make sense as just a sort of a general understanding of what's going on here?
Yeah, that's the same as the last one too, where we're just assuming the left side so that we can prove the right.
Correct. Absolutely. So we're going to assume the left-hand side and then prove the right-hand side. Yes, spot on. Okay. Now, from a computational standpoint, right, this is one of these places where if you have your, and most of your computer science majors, not all of you, but most of your computer science majors. So if you kind of think about this from a computational standpoint, one way to think about this is if I have a k that works here, it would be nice if I could compute in some way the k that made this work. Like if I had a little machine that I could say sort of, you know, k for p of n goes into my machine, and out came k for p of n plus 1. Right? So I had a little computational machine that could do that. Right? That would be a computational way to think about this, is that if I can give you a k that works here, can you do some computation, some algebra, some algorithm, whatever, and it cranked out the k that worked here. Then you would know that for any n, that you've got this little machine and you can put the k in for n and you get the k out for n plus 1, and that would give us the ability to construct these stepping stone proofs, right, that take us from n to n plus 1. This little machine would be cranking out these little proofs here and here and here and here. It would give us these little pieces that we need. And if we had something like that, that would be sort of nifty. This is not how a mathematician might necessarily think about this. Some would, some wouldn't. But I think sort of computationally, this is a nice way to think about it, is that can we take k here and use it to give us the k we need over here, okay? And so as a way to think about that in this example, if we make a little table, so let's say 0, 1, 2, 3, 4. So 4 to the 0 is 1. 1 minus 1 is 0. 4 to the 1 is 4, minus 1 is 3. 4 squared is 16, minus 1 is 15. 4 to the third is 64, minus 1 is 63. 4 to the 4 is 256, minus 1 is 255. And the fact that I knew that 4 to the 4 was 256 is proof that I spent too long in computer science, because most people don't memorize that. Now, and obviously this goes on and on and on, right? And the claim here is that this is a multiple of 3, which we're formalizing as there is some k where this is 3 times k. Well, 3 times what is 0? Well, 3 times 0 is 0. We kind of did that in the base case. 3 times what gives us 3? Well, 3 times 1 gives us 3. 3 times what gives us 15? And notice I'm just dividing by 3 here. Divide 15 by 3 and I get 5. Divide 63 by 3, I get 21. Divide 255 by 3 and I get 85. Okay. So this is all just me doing a little arithmetic. Oops. We haven't actually gotten to the interesting part yet. Are there questions about my little table? Okay. Now, then, if I think in terms of like my machine, what I kind of want is some way of going, if I know this, I can figure out what this is. And if I know that, oh, I've got some things happening in chat I should be paying attention to. Oh, okay. If I know 5, it would let me figure out 21. If I know 21, it would let me figure out 25. So can anybody see some sort of pattern where you could talk about, well, how do I get 21 given 5? How do I get 85 given 21? Is there some pattern that sort of takes me from k to k plus 1 in each of these cases? It's totally fine if you don't see one, but if you do, holler. Anybody?
Four times k plus 1.
Yeah, exactly. Good job. So each of these is one more than 4 times the previous one. So this is 4 times 0 plus 1. This is 4 times 1 plus 1. This is 4 times 5 plus 1. And this is 4 times 21 plus 1, right? So each of these parts is the previous value. And then we multiply by 4 and add 1, and that gives us the next value in this table. So one thing if this pattern turned out to be true, this would tell us that in general, 4 to the n minus, minus sign in the wrong place. 4 to the n minus 1 is 3 times 4 times 3 times, let me do this right. It'd be divided by 3. Sorry. Oh, I should have had a plus 1 here. Is 4 to the n minus 1 divided by 3 plus 1. So we're saying that at each step, we've got our old value, we divide it by 3, multiply by 4, add 1, and then we multiply that by 3, and that's going to actually give us our next piece. Now, we don't have to actually do all this stuff. And in fact, in your proofs, you're never going to make a table like this. I mean, you could, but you're not expected to or required to. I'm just trying to show that there is this way of computing the next k from the previous k. And that we could then, if we did this first, we could do our induction proof basically by proving that this is true for all n. And then that would give us that there exists a k, blah, 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 blah. But we're just going to sort of stick to proving this thing here. I just want us to understand this idea that there is a way to go from the previous k to the next k. That if I give you the k that works for n, there's a way to compute the k for n plus 1. And we'll, in fact, solve for that in the same way that we solved for the base case on the previous slide. I'm going to back up one. Here we solve for E. We're going to do the same kind of thing in the induction step, as we're going to solve for E, which E will be the k for n plus 1. And it turns out we're going to get this rule. We're going to get 4 times k plus 1 to tell us that, oh, that's how we go from the previous k to the new k. So, but instead of having to guess it, which we had to do here, we will actually use algebra to find it, which is much cooler than guessing. Guessing's hard. Guessing takes work, and then you never know if you got it right. If you guess, it's like, well, maybe it was true for these few cases, but maybe it's not going to be true in the future. Whereas if we derive it by doing a solution, then we know it's true. We know it's always true. And that's a far more powerful thing. So we will, on the next slide, actually do the induction step, and we'll solve for the new k, and we'll find that it has this pattern. And that's going to be, for me, kind of nifty. Okay? So questions about this before we move to the next slide and actually like do the induction step? Cool. So on to the actually doing the induction step. Induction step. So P of n implies P of n plus 1. Oh, man. P of n plus 1, i.e., there exists k in the integers where 4 to the n minus 1 implies exists k in the integers. Oh, man, I really got ahead of myself here. This wasn't even valid because this is not a Boolean valued expression. Also, it doesn't refer to k anywhere. There's a whole lot of things that weren't good about that. So equal 3k implies exists k in the integers 4 to the n plus 1 minus 1 equals 3 times k. Okay, so here's our goal. So by 9.30, this is true if and only if. So 9.30 tells us that if we have an exist implies something that we can, so this is witness, we can replace the quantified variable with the little hat dude. So this tells us that we can rewrite this as 4 to the n minus 1 equals 3 times k hat, where k hat has to be some totally new variable. That implies exists k 4 to the n plus 1 minus 1 equals 3 times k. So that step was important because it got rid of the exist on the left, which will simplify our lives in some significant ways. And I'll say for new k hat, for new variable, it's important that k hat not appear anywhere else in the problem, which it does not, so we're good. So if we assume the left-hand side, then our right-hand side says there exists k in the integers such that 4 to the n plus 1 minus 1 equals 3 times k. Now, this by 9.28, just like we did before on the base case, this follows from 4 to the n plus 1 minus 1 equals 3 times e. And I'll say over here for some integer expression e. So we got to remember that it needs to be an integer. Okay. So now the trick is, can we find an e that works here? So if we back up, I'm going to back up 2 slides. So here we got to here, and then it was a question of finding an e, using algebra to find an e that made this true. And so we're in exactly the same position now. We've gotten to here, and the trick is, can we find an integer expression e that makes this thing true? And we almost certainly need the induction step. Like, why would we have bothered doing induction if we weren't using the induction step? So we've assumed the left-hand side, right? So we've assumed this here. So we really probably need to use it. And the trick here is actually to notice that we can make this match this. So we can do a little algebra, and we can rewrite this as 4 times 4 to the n minus 1 equals 3 times e. And now 4 to the n, and this is, I'm doing kind of a little math off to the side here. This is equivalent to 4 to the n equals 3 times k hat plus 1. I can move this 1 over here by a little algebra. And now I can rewrite 4 to the n as this expression involving k hat. And that seems like that's probably a good thing, because k hat is the value that worked here. So I'm kind of trying to find something that probably uses k hat for my expression e. So here I use the induction hypothesis. And this is perhaps the most important step. Well, I mean, they're all important, or that thing doesn't work, but this is sort of a really central step in this proof. So we have 4 times, well, 4 to the n is 3 times k hat plus 1 minus 1 equals 3 times e. And now I can do a little algebra. And I get 4 times 3 times k hat plus 4 minus 1 equals 3 times e. And now I'll do a little arithmetic. And I got 4 times 3 times k hat plus 3 equals 3 times e. Okay. Now, this is, I think, the next kind of significant step in the proof. Like, you know, this was just grinding away through some basic algebra stuff. Here, we want to get, we're trying to solve for e. And if, like we did before, it would make sense to just divide through by 3. The trick is we need to know for sure that e is an integer. The nice thing is that here we know that will be true because this is divisible by 3. It's got a 3 in it. And this is divisible by 3. If we didn't have all of these pieces divisible by 3, like I could have divided by 3 way back here. but I don't know that this is a multiple of 3. So that doesn't tell me that E is going to be an integer. And I don't know that this is divisible by 3. So if I divide through, I don't know that E is an integer. I don't know it here yet either. I don't know it here either. But here I have finally rewritten this, and that's part of why I did the algebra and arithmetic stuff. Here I've got a 3 everywhere. And so I can divide through by 3, divide both sides by 3. And I'm going to get something that I know is an integer. Because this was an integer, because it was the hat dude here, and this is going to have the same type as the quantifier type. So this was an integer, so this is an integer. 4 times an integer is an integer. Adding 1 to an integer gives you an integer. So E is an integer. And that completes the base case. And this is the thing that we had to discover on the table, that somebody had to kind of take a flyer at and guess that the next one was 4 times the previous one plus 1 on the table. Well, here we don't have to guess it. We actually just derived it using math, which is way better than guessing. Now we know this is true for all n, not just the first 5 entries in the table or whatever I had there. So this is a much sort of better way of doing this than doing the table and guessing, because now we know for sure that this will be true for all n. And if we care computationally, how do we build the next k out of the previous k, this tells us how to do it. We may not care. Maybe all we care about is that 4 to the n minus 1 is a multiple of 3. But if for some reason we do care what the k's are, this would allow us to build the new k out of the previous k, as we sort of go through the numbers, if we care about that. So, so that completes the base case and QED. Wow, crowd goes wild. Now that's a lot. There's a lot going on there, and I would certainly love to take a question or two. We've got 7 minutes, so we certainly have time.
What do you mean by that completes the base case?
So, great question. So we had assumed the left-hand side, and we needed to prove that the right-hand side was true. Does that part make sense?
Yeah, I get that part.
Gotcha. So then we started with the right-hand side. The right-hand side followed from something which was equivalent to, oh, these are all equivalents here, was equivalent to something which is equivalent to something which is equivalent down to here. Okay? This, because E is an integer, this is true. If we've solved for E, we have found a value that makes this true. And this was, at this point, all we said was that E needed to be some integer expression. And we didn't care what it was as long as it was an integer. Well, we have found an integer value that we can use for E. So this is true, which is equivalent to true, 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 which implies the thing that we want. And true implies P equivals P by some chapter 3 rule.
Doesn't that mean we complete the induction step as opposed to the base case?
Oh, yeah, totally. If that was the question, yes, I completely biffed that writing. Thank
Yeah,
you.
that's what I was asking. Yeah.
Oh no, you people are much smarter than me, and you actually are paying attention. So I'll go ahead and write 373 here just for the fun of it, and then we'll fix the mistake that I made because that is clearly wrong. You know, yeah, that was totally the induction step. I'm a doofus. Induction step. Yeah. So that completed the induction step. We'd already done the base case. So
Okay,
now
well,
that
that
we've
was all
done
I
the
was
base
wondering.
case and the induction step, we're done with the proof. That sort that out?
Yep.
Cool. Sorry about that. Good
No,
catch.
that's okay.
Well, thank you for mentioning it. You know, I'm glad that we got that fixed. So, whew. Other questions?
So, are most problems going to have either an expression where you have like some kind of function, or was it going to be like a solid number answer?
So the exists problems tend to look like this. So, which is the divisibility problem, and there's one of those on the homework. And then there's also some problems, one of which will be on the next homework, and that would be what we would move to next. But there probably won't be time today, so we'll do it Wednesday. There, your next one of the problems on the next assignment is 12.14, which is showing that you can make anything bigger than 14 with 3-cent and 8-cent coins. So if you lived in this weird universe where there were 3-cent coins and 8-cent coins and nothing costs less than 14 cents, I don't know why that would be true, that you could make anything out of 3-cent and 8-cent coins as long as it was 14 or higher. That's also will turn out to be an exist proof. And so it will look like this. But all the up till like the less than proofs and all of the like the summation proofs, none of them are as complicated as this because none of them have exists in them. It's when you have an exist problem that all this witness and instantiation stuff comes in. So the divisibility problems have exists in them, and the coin problems have exists in them. So they'll have this form, but the other problems, like the summation problems, they don't have any of this exist stuff, so they won't have this form at all. Did that answer the right question?
Yes, thank you.
Okay.
Have we done like division problems, or
What?
have we done division problems?
Divisibility problems? That's just what this one was. So, because we were showing that 4 to the n minus 1 is divisible by 3.
Yeah, okay, yeah.
And we formalize that as an exists. So whenever the formalization of the problem is an exists, then we tend to get this whole weird structure. And that's true for in the book, there's the problem saying that 2 to the 2 times n minus 1 is divisible by 3. And then there's this problem. And then there's a problem that 10 to the I minus 1 is divisible by 9. And then there's the problem that x to the n minus y to the n is divisible by x minus y. So all of those are going to have this form. And then the coin problem on the next assignment will have this form. But the other induction problems will not look like this. They're not as complicated. These are, in a lot of ways, the hardest, or certainly the most structurally complicated induction proofs that we'll do. Other questions in 1 minute?
The assignment for today is due at 10 p.m. tonight.
I don't remember. Did I say tonight or tomorrow night? I think
I said it was due tomorrow.
I think I meant to say tomorrow night. I'd have to look it up. Let's look it up quick just to be 100% sure. And if I didn't say tomorrow night, then I will fix it because that was my intention. Oh, I did. It's actually listed as tonight, and that was not my intention. So I'm going to actually change that. My bad. I think I changed the time and I didn't change the day. So I just changed that in Canvas. That's due tomorrow night at 10.
All right.
So thanks for asking. And then I'll post problem set B and chapter 12 problem set B, and it'd be due a week from Tuesday. And I think we'll be okay with that. I think we can get through things to be in a reasonable place to have that due next Tuesday. But if things move more slowly than I expected, we can push that one as well. So, other questions in the 0 minutes that remain? Okie dokie. Well, thank you all very much. And I will see everybody on Wednesday. If you have questions about the homework, definitely hit me up on Slack or email or whatever, or office hours, and we'll see what we can do. Talk to you later. Bye.